We're going to learn about composite bodies, and in particular, how to locate the centroid of composite bodies. So if we've got some shape that's not simple, how do we locate the centroid of that shape if it's an area, for example? Or if we have multiple bodies, say on a platform, how do we locate the centroid or the center of mass or the center of gravity of all those items? Well, we're going to learn how to do it. Of course, there are extra things you should go through, the examples in these slides, for example, my example problem videos as well. But primarily, we're going to look at the method of composite bodies, and it's useful for multiple situations. So here's an application where we have an I-beam or even a T-beam, and when you're performing stress analysis on something like this, when you get to strength of materials with me or with another professor, knowing something about the cross-sectional properties is absolutely critical. In fact, there are more properties than you're going to learn here, but the one basic thing you need to know how to do is locate the centroid of an area. So you can see the eye area there, and of course, since that eye area is symmetrical, you know that, well, it actually has two axes of symmetry. You know that the centroid simply lies at the middle of that I shape that you see. But what about the T shape? How would you locate the centroid of that? Well, you might realize, well, if it was just the upper rectangle, that's easy. I know where the centroid is for that upper rectangle. If it's just the webbing in between, that vertical piece is called webbing. If that was all that was there, then I would know where the centroid is located. How do I do this when I know the centroid of two simple shapes? Well, that's where composite bodies come into play. That's what this is. It's the wooden beam there, a T-beam, is made of two bodies or two cross-sectional areas. Both are simply rectangles. So the method of composite bodies will allow us to locate the centroid of this T shape as a whole. Of course, the I shape is trivial technically because it is, at the centroid of the two, or at the intersection of the two symmetrical axes. But for the T shape, it's a little more involved. There are other applications. For example, if you've got some type of a skid with a whole bunch of different pieces of equipment, and each piece of equipment has some significant amount of weight because of its mass, then locating the balance point is critical, because if you've got to pick this up and you've got to rig with it, you need to know how much load is going to be applied. Let's say you're picking it up at points A and B, and you need to know how much load is on points A and B so you can keep it stable and horizontal as you lift it. Well, understanding how to use the method of composite bodies is really important so that we can locate the center of gravity and therefore how much weight would be on the feet. So if we know the center of gravity of each of the individual components and how much weight each has, then we can actually calculate the location of the assembled unit center of gravity. So for a composite body, the idea is actually pretty simple. It's very much like what we did with a single body, but in that case, remember, we integrated over the entire body or over the entire area. In this case, we don't have to integrate. We're basically going to do exactly the same thing, but this time we've got a finite number of bodies to deal with. So all we have to do in order to find a balance point, we're looking for the point where all of the weight together, for example, could be concentrated at that point and have the same moment about a given axis that the individual components have. And so the equation is actually very much like what we had before, where we said that the moment of the resultant, in other words, the moment of all the weight, so the location of the centroid, x bar, multiplied by the combination of all the weight, w sub r, it should be equal to the moment of all the individual bodies about the same axis. So x bar, or well, not x bar, but x tilde 1, w1, plus x tilde 2, w2, so on and so forth, to however many bodies we have. And all that x tilde represents is the same thing it did before, except now it's an individual body rather than a differential bit of a single body. And not surprisingly, the form of the equations come out almost identical. Really, the only difference between the last section and this is that we've replaced an integral sign with a summation sign. And honestly, the two are very similar to one another. The only real difference is here we have a finite number of bodies to add up over. So that denominator is just all the weight added together, just like before. The integral of all the weight was dw in that case. So it's just the total weight. Now, of course, we can replace any of these, in any of these equations, we can replace the weight with, say, area or volume or mass or length or whatever is needed for the problem that is given. But the idea is that we've got individual elements where it's easy to find out the location of the centroid of that element or the center of gravity of that element and the amount of weight or area or volume that that particular element contributes to the total. So now let's look at some areas where we'd like to know the centroid of an area that's a little more complicated than what we've dealt with so far. For example, the figure on the left has a triangle, okay, triangle at C, and we could locate the centroid of that triangle. We could calculate the area of that triangle very easily. So the weight, if you will, or the area of that triangle is pretty easy to calculate. You've probably been doing that for a while, just 1/2 base times height. You can see the section B. If it weren't for the bit that's taken out of it that's labeled D, B would just be a square or a rectangle. Yeah, it looks like it would be a square. Calculating the area and locating the centroid of that square is really, really easy, right? So that's another individual contribution. And then there's a semicircle off to the left labeled A. And that semicircle is almost a perfect semicircle, except again, something's taken out of it. And so what we could do is locate the centroid of those three individual bits of area or pieces of area. And here's the interesting thing, where we've got that circle taken out, we can add that in as a negative amount of area and use it to offset the centroid a bit, and thereby calculate the location of the centroid of that entire body. So we can break down more complicated shapes into simpler shapes and use information about how much area or weight or whatever it may be that each has, and the known, location of the centroid of each of those pieces, take the moment of each of those and therefore find the centroid of the more complicated shape, or in this case, area. So basically all we have to do is consider each of these parts as like a particle. In other words, all of their properties concentrated at one point at the centroid of that particular body or area, and then use the procedure very similar to what we did in the previous section. So this is a very easy way to find the centroid or the center of gravity of a more complicated machine or area or whatever we're trying to deal with. So here's a step-by-step procedure. Divide the body or shape or whatever it is into pieces where it's easy to calculate properties like area or weight or whatever the case may be, and locate centroid for each of those individual pieces. Now, as we said, holes or things that are missing are really like shapes that have negative weight or negative size or negative area. And so that's a common technique for, dealing with holes in parts. Then it's best usually to do all of this in Excel. If you don't know how to use Excel, you should get used to it, because it'll make your life a whole lot easier. And you'll see me use Excel extensively in the example problems, and I'll try to show you some Excel tricks as we go as well. But it's best to make a table to keep all this data straight, because you're going to have a property, like let's say we're dealing with an area, you're going to have the amount of area for each shape. And each row then could represent each individual area. You need the X typically and Y location of the centroid of each of those individual shapes, and wouldn't it be nicer to have Excel do the math for you anyway? So all the intermediate calculations, in fact all the calculations, can be done in Excel, which is really nice, because Excel is just basically a differently advanced calculator than, say, your graphing calculator. And as an engineer, you will use Excel extensively, so you may as well just learn how to do it now and make your life easier. So we've got to decide on a coordinate system and, of course, locate the coordinates of the center of gravity or the centroid for each of the pieces. So then finally, we just sum the columns to get X bar, Y bar, Z bar by using the formulas, and it's pretty easy. I know this list seems a bit confusing, and maybe the idea is a little bit confusing, but I think with some examples, you'll see how easy this is. But do yourself a favor and learn to use Excel for this stuff, because it'll save you a whole lot of time. It'll help you not make a lot of errors too, and that errors in a problem like this can be frustrating because there's so many equations to run through. It's very tedious, even with a relatively small problem. So do yourself a favor and learn to use Excel.